Okay, in an example here, we're going to talk about how we can use torque in a static situation to predict two unknown forces and in a situation where maybe we wouldn't have been able to predict both of them. So we have a bridge spanning a small gap of 4 meters. The bridge is 45 kilograms. The bridge is supported on each end by a base. You, 65 kilograms, decide to walk across the bridge. What is the force in each base when you are 1 meter from the end of the bridge? So there's a base, there's a base, and this is going to represent our bridge. Our bridge has a mass of 45 kilograms. And then there's you. This was 4 meters. And you are 1 meter away from the end of one bridge. And just for the sake of having a common mass, your mass is now 65 kilograms. Okay, so what we're going to do here is we're going to use two things. We're going to find the force in this base, which I'll call A, in this base, which I'll call B, just to keep them separate. To do that, we can recognize a couple things about this system. Number one, if it's going to be static, if it's a bridge and it can't move, then the forces must add to zero. But also, if a bridge isn't going to fall down, it can't just not translate up or down, it also can't rotate. So the secondary thing we can use here is that the torques must add to zero. So what I'm going to do, and I can pick any rotational point I want because there is no point at which it would be okay for this bridge to rotate. So any point I want to choose is acceptable. So what I can do is I can pick a point cleverly to make one of my forces not appear in the equation, and then I can consider the torques of all of the other points, and by adding them to zero I can determine what the force is. So the clever point I'm going to take first is this point at A. So I'm going to do the torque, and I'm going to do the torque about A. So I'll put a little subscript A there to tell me where my rotational point is. Now, one object, U, so the force of the person times the radius of the person, so that's one torque. And then we're going to have the radius of the bridge times the force of gravity on the bridge. I don't want to call it B because that's confusing with B. I'll call it, I'm kind of blanking with something else to call it besides a bridge. I'll call it force of the wood. Let's imagine this is a wooden bridge, okay? And then finally, so that's this force pointing down, and then this force pointing down, the mass of the bridge. And then finally I have a force pointing up here, FB, about a rotational point, or at a radius of B. So I consider all these forces and radii, and they all have to add to zero so that this thing won't rotate. Now, first of all, the radius of the person is 1 meter. And the force of the person, what we mean here is the force of gravity acting on the person, will be 9.8 newtons per kilogram times 65 kilograms. The radius of the bridge, we're going to assume that, or the wood, we're going to assume that the wood's mass is evenly distributed throughout, and so it's acting at a distance of 2 meters. And again, it's the force of gravity acting on that piece of wood that we're interested in. And finally, the linchpin B, or the base B that's pushing this bridge back up, sorry, these should be negative 9.8s, is acting up, so that's the force of the bridge, and its radial distance is 4 meters. So now I have an equation that I can solve for the actual force in the bridge. So 65 times 9.8, so I get negative 637 Newton meters plus 9.8 times 2 times 45, 882, so negative 882 Newton meters, and 4 times FB. Now I'm going to move all these guys over, so I'll get 637 Newton meters plus 882 Newton meters equals 4 FB plus 637. So I got 1519 Newton meters equals 4B. And then if I divide both sides by 4, I get the force at B to be 379.75, or basically 380 newtons. Okay, so since I can't let this thing rotate about any point, I chose this point. I chose this point because when I consider all the torques acting in that point, what happened, I forgot to mention this at the beginning, is that I should have included RA and FA. But I don't need to, because this point is in line with A, RA would be 0. Which means this term, which includes one of my unknown forces, disappears. So working from this point, I can easily come up with the distances of all the other forces and the magnitude of 2 of the 3, and so the third one I can solve for. Again, the force of gravity pointing down, that's where that negative came from. 45, force of gravity pointing down. And then 4. Since it can't rotate, all of those torques have to add to 0, and I end up with an equation that's solvable for FB. To get FA, I have two options. I'll do both. I can consider the rotations about point B the same way I did for A, and I'll end up with an equation just like this one, but it'll be slightly different. Or I can look at the sum of the forces in the vertical direction. So let's do the sum of the forces in the vertical direction first. If this is going to be a static situation, it has to be 0. So that's going to be FA plus FG from the person plus FG from the wood plus FB. And now I know all of these, so I'm just missing FA. I can solve for FA. FA plus, this one was 9.8 negative newtons per kilogram times 65 kilograms plus negative 9.8 newtons per kilogram, 45 kilograms plus 380 newtons that I found right here. Okay, so FA minus 637 newtons minus 9.8 times 45, 441 newtons plus 380 newtons. 637 plus 441 minus 380 is 698 newtons minus 698 newtons. $698 newtons. Okay, so that's using the sum of the forces. That's pretty straightforward. But I can do these questions where there's two ways to get something and they're independent of each other are really nice, because I can do the second way and then that'll serve as a check to see that I haven't made any mistakes in this problem. So let's go ahead and do that. So I'll do the torque about B. Now I have RB and FB, which I don't need to include because RB is 0, so that one doesn't matter. I have R wood, force of the wood, that's the wood associated with the bridge, plus R of the person, force of the person, plus RA, FA. And all of that has to add to 0, so this thing won't rotate. So R wood is going to be 2 meters times negative 9.8 newtons per kilogram times 45 plus R of the person. Now careful here, since I'm going from this side, this person is now, if this is 1, this is 3 meters away from point B. Times the force of the wood, which will be negative 9.8 newtons per kilogram. And the mass, not the force of the person, sorry, and that's 65 kilograms. And RA is 4 meters away times the force of A. Okay, and that's all equal to 0. So I've done this one already. It worked out to 882 Newton meters negative. This one is going to be 637 times 3. 1911 Newton meters negative. And 4 meters times FA. So I'm just going to collect those like terms. 2793 Newton meters plus 4 meters negative. So 4 meters equals 2793 Newton meters. Force B. Or no, A. It's A. Yeah, sorry. A. Dividing both sides by 4. I get that FA should be 698 newtons. So I found FA in 2 separate ways, and it turned out the same number. So I'm pretty confident that I haven't made any mistakes while doing this problem, which is always a nice thing to be able to check when you're doing something like a test. So that is how you can use torque to find 2 unknown forces on an object. A pretty straightforward example. You can imagine this example could get a lot harder if the forces were acting on angles or stuff like that. And I might put a video or something like that up eventually, but right now, at least if you're in my grade 12 class, I won't be asking you to do that problem because it gets a little tricky. All right, I'll do another one where we add a force to balance a system next.